All right, so for us, today we're gonna spend all day talking about how to solve exponential equations and log equations. So we're gonna start off with exponential equations, and all of the directions are gonna be the same today. We're gonna solve these for x. So let's just dive right in. So if I have 2 to the 3x minus 8 is equal to 16. All right. First of all, this represents an exponential equation. Why? Why is it an exponential equation? Yeah, because the variable is up in the exponent, right? That's exactly where it is. So the trick for this particular type of a problem is there a relationship between the bases, right? I have a base of 2 and I have a base of 16. So the question is, can I write 16 as a base of 2? Yes, I sure can. What would it be? You got it. So 2 to the 3x minus 8 is now equal to 2 to the 4th. This is good news for us because if our bases are the same, what does it tell us about the exponents? They equal each other. Nice job. So that must mean that 3x minus 8 is equal to 4. So that means that 3x is equal to 12. So x must be 9 to the x minus 1. All right, 27 to the x plus 3 equals 9 to the x minus 1. Again, we have an exponential equation here because our variable is up in the exponents. And we want to solve for x. So, is there a relationship between 27 and 9? Can we write them in the same base? Yeah, we sure can, right? So that'd be 3, what? To the what? Very good. 3 to the 3rd to the x plus 3 equals 3 squared to the x minus 1. Yeah, now we're going to have to distribute this. So make sure that when you multiply, when you raise a power to a power, you need to multiply them together, but you need to distribute out your 3 and your 2. So you'll have this. 3 to the 3x plus 9 equals 3 to the 2x minus 2. Good news for us, bases are the same. That means that the exponents must be equal to each other. So then I got 3x plus 9 is equal to 2x minus 2. So x must be 4 to the x minus 3. 8 to the x plus 2. All right, here we go. So I still have an exponential equation. I have 4 to the x equals 15. What's the only difference here between this problem and the one we did before? There's no base? Well, there's a base there, yeah. Yeah, there's no common base, right? There's no, you okay over there? Yeah. Okay. Yeah, 4 and 15 don't have a common factor that we could write their bases as. Okay, so what do we do? So, is there any way we could change this from exponential to log? Yeah, what do you think?
If you did log base 4 of 15 is x.
Yeah, so there is a rule. We have one of these properties in logarithm that says that a to the log base a of b will give you back b. Okay? That is a rule of logarithm. That's one of our properties that we've seen before. But in a more just sort of straightforward approach, we could change from exponential to log form and say, well, x would have to be log base 4 of 15. Right? That's the exact same thing. These things are essentially saying the same thing. Okay, so the question then is, this is the exact answer, but how do I solve this, log base 4 of 15? Well, we're going to use our calculator to help us out. You can either use the change of base formula. You have two options here. You can use the change of base formula, or you can use, math alpha math. If you have the fancier calculator, the newer versions, okay? So either way, you're going to get log 15 divided by log 4 if we use the change of base formula. Or if you could use math alpha math in your calculator, you can get that as well. I don't have the math alpha math key strokes in my calculator, so I'm going to use the change of base formula. So that means that you can use the change of base formula for anything. So I'm going to say log 15 divided by log 4, and that gives me a 1.95. So whichever one you're going to use, doesn't matter to me. Just make sure right now you can evaluate log base 4 of 15 in some way, either on your calculator with the change of base or by actually plugging in log base 4 of 15. And we should all get the same answer of 1.95. So x is approximately 1.95. Now, what is the meaning of that? Someone interpret that for us. What does 1.95 mean?
4 to the 1.95 power would equal 15.
Very good. If we check 4 to the 1.95 power, we should get approximately 15. And when you do check your answer, 4 to the 1.95, you get approximately 15. So if we round to 2 decimal places, we'll be good. Okay. Okay, we'll call this A. Try this one here. 5 to the what power would have to... Does that come full circle for you, Maddie? All right. Okay, so 5 to the log base 5 of 134 gives us 134. We evaluate log base 5 of 134 in the calculator, either using the change of base formula or plugging straight in. And I got 3.04 for x. Do you guys get that? 3.04. Okay, you guys try it in your families. 3 to the what? This is a little bit more funky. What's different about this one? Yeah, it does have exponents. It's still an exponential equation, but what's different?
No common base.
There's no common base, and there's x on both sides, okay? So the way that we get ourselves out of this is we have to use the change of base formula, but since we can use any base that we want, I'm going to take the natural log of both sides. I could take the log of both sides, doesn't matter, but natural log is shorter keystrokes, so I'm going to take the natural log of both sides. So here's what I mean by that. I'm going to take the natural log of 5 to the x minus 2 equals the natural log of 4 to the 2x plus 3. If I take the natural log to both sides of my equation, I still hold true to my exponential as I started with. All right, there's a very, very specific, important reason why we would take the natural log of both sides. It allows us to do something very useful. Anybody know what it is? Can anybody see it? Has something to do with the rules?
Cancel.
No, not cancel.
Why can you just throw it in a natural log?
You can put in a value. The loggy.
No, not that. I'm taking the natural log of both sides, so I'm essentially doing the same operation to both sides of my equation. Because she said, how can we just throw a natural log in there?
If you do same thing to both sides,
Anybody understand the power rule? Power rule? Yes, what do you see, Albert? Yeah, check this out. This is the cool part of it. This is an exponent, right? It can be plopped down in front. This is an exponent, right? The whole thing can be plopped down in front because of the power rule. So this is very useful to us because then we get an x minus 2 times the natural log of 5 equals a 2x plus 3. You got it. We're going to distribute our natural log 5 and our natural log 4. So I'm going to distribute this, and I'm going to distribute this. To get, here's my line of algebra. X times the natural log of 5 minus 2 times the natural log of 5 equals 2x times the natural log of 4 plus 3 times the natural log of 4. So see how chunky that looks? But the natural log of 5 is just the number 1.6, and the natural log of 4 is just the number 1.4, right? We're gonna eventually, but we have to isolate the x, right? Remember, our whole goal is to get x by itself. I'm gonna highlight for you the terms that have an x in them. Yeah. Well, 1.6 is an approximation. We want to keep it exact throughout the whole entire problem until the very end. But essentially, it's all it represents. It represents a number. But 1.6 is an approximation of that, right? What's going on over there?
that's multiplication.
No, it's a minus sign.
Oh, yeah.
It's a minus sign. All right, so remember, the goal, you guys, is to get x by itself. So on the left-hand side, I have an x natural log 5. On the right-hand side, I have a 2x natural log 4. And then I just have these other numbers, right? I have this other number here and this other number over here. So I want to get all the terms that have x to one side and all the terms that don't to the other side. So I'm going to have x natural log of 5 minus 2x natural log of 4 equals 2 natural log of 5 plus 3. Okay, so now, if I want to get x by itself, notice I've got an x here and I have an x here. So there's an x that's common to both of those terms. Therefore, I can factor out the x to give me this. X times the natural log of 5 minus 2 times the natural log of 4 equals just what I have right now on the right-hand side. 2 natural log 5 plus 3 sides. Natural log of 5 minus 2 natural log of 4. So on the left-hand side, look, this entire number cancels with that entire number, or it has a factor, multiplies to 1. So all I'm left with is x is now approximately, okay, I need to plug this exact value into the calculator. I'm going to show you how to do that right now. It's very important you follow along. That's not right. Hold on a second. Hold on. I'm dividing by natural log 5 minus 2 natural log 4. Alright, here's how you plug this in your calculator, and here's how you not get it wrong. You need to put the entire numerator in a set of parentheses. So we're going to start with a left parenthesis and plug in 2 natural log 5 underneath log, close parentheses, plus 3 natural log 4, close parentheses, and then close your parentheses. That's putting the entire numerator into a set of parentheses, right? And notice pushing natural log 5 is more accurate than pushing 1.6. That's why we're saving it till this step in the whole problem. Then we're going to divide because we have a quotient. Same trick on the bottom. We're going to put parentheses, natural log 5, close parentheses, minus 2 natural log 4, close parentheses, close parentheses. If we do this right, we should all get negative 6.34 and some change. Oh, there it is. All right? That's how you do it and get it right every single time. Because I don't want you guys to do all this work, then get to the end, and then get like a calculator misstep.
How far are you on this?
We're going to go to 2. At the very end, we're going to go to 2. The very last step. So negative 6.34. Negative 6.34. Okay, you guys, in your family, this one's on your own. Try it. 3 to the 2x minus 1 equals 7. So I'll put up there for you. All right, this is a log equation because it's an equation that deals with a logarithm. All we really need to do is understand the relationship between how to change a log form to an exponential. So if I'm given a log form, how would I change it back to an exponential? What would we do? Yeah, we would just go 4 squared gives me back x plus 3. So I'd have 4 squared equals x plus 3. All of a sudden, I have a very, very simple equation, right? I get 16 is equal to x plus 3. So x has to be 13. That's not so bad. Okay, let's do one more here. What if I have 3 natural log of 2x is equal to 12? 3 times natural log of 2x is equal to 12. Okay, think of the natural log of 2x as just a number for a second with a variable in it. So I have 3 times the number times x equals 12. What would you do first if this was just a regular old algebra problem? Divide by 3, yeah, exactly. If I divide by 3, I get the natural log of 2x is equal to 4. 12 divided by 3 is 4. All right, looking better so far. Now, what is a natural logarithm? It's a log with a base of e, huh? So I could rewrite it as that, log with a base of e. Oh, now how do I get myself out of this situation? You got it. E to the power of 4 gives me back 2x. So e to the 4th equals 2x. Oh, this is super rad. Divide by 2. So that means that x is equal to e to the 4th divided by 2. You can leave it like this. This is the exact answer. Or you could get the approximate answer. X is approximately 27.3 when you run that through your calculator. Okay? Doesn't matter to me. Exact is good. Or if we're going to do any rounding, we'll go to 2 decimal places. So what would that be if we do it in 2 decimal places? E to the 4th. So second e to the 4th. And then divided by 2. So 27.30. Okay. Okay, we're going to finish up box 4 and box 5. So we'll do one more example here. If I have log base 2 of x minus 4 is equal to 3. Let me scoot down a little bit. Okay, we can say then that 2 to the power of 3 will have to give me back x minus 4. So we're going to have 2 cubed equals x minus 4. So 8 equals x minus 4. So x has to be 12. All right, that's easy enough. And then we'll do one more example. If we have 4 times the natural log of 3x equals 8, the goal is to get x by itself. I'm going to divide both sides by 4. I'm going to get the natural log of 3x is equal to 2. And then natural log is nothing more log with a base e of 3x equals 2. We can exponentiate. Say e to the power of 2 will have to give you back 3x. So e squared equals 3x. We'll divide both sides by 3. So the exact answer would be e squared over 3. The approximate answer will be 2.46 when you plug that into your calculator. Either one of those is fine. All right, let's talk about the 5th box now. The box I did not get a chance to get to because we had a short Wednesday. All right. The first one, part A. We're going to do log base 2 of x plus log base 2 of x minus 7 is equal to 3. All right, a little bit more complicated log equation here. First of all, I have log base 2 everywhere, and I'm adding, so I can condense that log base 2 of x times x minus 7. Because I can expand a logarithm over addition through multiplication, so I can condense in the opposite order. So therefore, I'd have 3 on the other side. Now, when I exponentiate both sides, I have 2 cubed equals x times x minus 7. So what I end up with is 2 cubed equals x squared minus 7x. So 0 equals x squared minus 7x. All right, so what we're left with is nothing more than a quadratic. So we're going to say 0 is equal to, well, we can factor this quadratic. X and 8 and 1. Let's see here, they both have to be minus sign here. Minus sign and a plus sign. So I can use the zero product property and say that x either has to be negative 1 or x has to be positive 8. All right, now here's where the thinking comes into play. It turns out negative 1 is what we call an extraneous solution. You don't need to know that, or what we call it, extraneous solution. All you got to know is realize that when you plug a negative 1 back in for x, and we try and evaluate log base 2 of negative 1, we get a domain error. And the reason is because think of the graph for log base 2 of x. We're going to have 1, 0, and then 2, comma 1. So my graph for log base 2 of x looks like this. X is negative 1 is not part of the domain because it's over to the left because I have an asymptote here. So negative 1 is what we call an extraneous solution. That means that 8 is the only solution. Okay, so when you see the directions, they'll say something like solve the log equation and check for extraneous solutions. That's what they mean. That's totally what they mean. Okay, so here we go. Natural log of x plus 2 minus natural log of 4x plus 3 equals the natural log of 1 over x. All right, so first we're going to begin by condensing the left-hand side into the natural log of x plus 2 divided by 4x plus 3. Because I am subtracting those logarithms, so I can condense through a division. Equals the natural log of 1 over x. Okay? So what I'm going to do is I'm going to say, all right, the natural log of x plus 2 divided by 4x plus 3 minus the natural log of 1 over x is now equal to 0. I have x's on the same side. Now again, since I am subtracting these two things, I can condense and say the natural log of x plus 2 divided by 4x plus 3, all divided by 1 over x, but that's the same thing as multiplying by x over 1, equals 0. So when you divide this and this, it's the same thing as dividing two fractions as taking the reciprocal of the second fraction and then multiplying it out. That's how I got that. Okay? So now remember, this is a log with a base e of x plus 2 over 4x plus 3 times x over 1 equals 0. So I'm going to bring this problem up here now. And I'm going to exponentiate. Okay? E to the power of 0 gives me back all this stuff. Excuse me. So e to the 0 gives me back x squared plus 2x all divided by 4x plus 3. All I did was I multiplied the x times the x plus 2. Well, e to the 0 we know is a value of 1. So 1 is equal to 4x plus, 1 is equal to x squared plus 2x over 4x plus 3. Multiply both sides by 4x plus 3, and you get this. 4x plus 3 equals x squared plus 2x. Well, again, all I have here is a quadratic. So when I write everything on one side, I get 0 equals x squared minus 2x minus 3. Yep, got that. So I can factor this. 0 equals, I'll have an x plus 1 and an x minus 3. Using the zero product property, x either is negative 1 or x equal to positive 3. When I check negative 1 back to the original equation here, check this out. It's not going to work right there because I cannot take the natural log of negative 1. Not going to happen. So that means that this one is an extraneous solution, so the only answer is x plus 3. All right, pre-calculus, there you go. Good luck. Talk to you soon.